Hello everyone. Hello everyone. Okay, it's 5 past 6. It's 5 past 6, and I will wait for another 5 minutes, and then we will start. Okay. Okay, let me start the session. So, welcome you all to this problem solving session of second week for the NPTEL course titled Multirate-DSP. For those who are attending this for the first time, myself Saurashis Chatterjee. I am a PhD scholar from IIT Kanpur, and today I intend to guide you through some mock problems that is going to be helpful to solve your assignments. So let us start. So today our first problem is uh, a continuous time signal xt is band limited to omega m. So what would be the minimum allowable sampling frequency for x t by 4 to avoid aliasing? So let us note down the information. First, x t is a continuous time signal. Ct means continuous time. So let me draw the spectrum of xt, which is denoted by xc of j omega. Omega is the analog frequency. So this is some arbitrary spectrum for some arbitrary xt, of course. So if xt is band limited to omega m, xc of j omega will look like this, minus omega m to omega m. xc j omega is going to be 0 for omega outside this range. That basically means xt band limited to omega m. Okay, so let us look at the signal x t by 4. So the question is, we need to find the minimum allowable sampling frequency for this signal xt by 4 to avoid aliasing. So let me draw a property of Fourier transform that says that if Fourier transform of xt results into this spectrum xc of j omega, then x t by 4, the Fourier transform would produce spectrum this. Oh, sorry, let me correct myself. Okay, this comes from the time scaling property of Fourier transform which says that if xt is going to have a spectrum denoted by xc of j omega, then x at is going to have this spectrum. As you can see, this is a scaling amplitude scaling factor, and this is this frequency domain scaling. Now if I try to find the correlation between this and this, let us denote x t by 4 as x tilde of t, then its spectrum, Fourier spectrum, is going to be xc of j4 omega. So let me draw the spectrum of xc of j4 omega. As of now, I am not considering this scaled amplitude factor 4. You can add this anytime. This we can correspond to like this: omega m by 4 minus omega m by 4. How I arrive at this conclusion? Because you see, in this scale, if I put omega dash is equal to omega m by 4 times 4, we are getting omega m. So if xc of j omega has spectrum this, xc of j4 omega is going to have this spectrum. So we can see that the width previously was 2 sigma m, now it's sigma m by 2. So this spectrum is contracted or squeezed in frequency domain. So now it's maximum frequency component is equal to omega m by 4. I'm talking about this xt by 4 has maximum frequency component omega m by 4. Therefore your sampling rate omega s, let me denote this maximum frequency component as omega m dash. So your sampling rate should be greater than equal to twice sigma dash m, which is nothing but 2 times omega m over 4, which is omega m by 2. So you need to sample, your minimum sampling frequency should be omega m by 2 to avoid aliasing for this signal xt over 4. Okay, so let us move to our second problem, which says xz is the, okay, let me correct. Okay. Xz is the z transform of xn and yz is the z transform of yn. Now if yn is the upsampling version of xn with upsampling factor of 3, which of the following holds true? So according to the question, xn, if you perform z transform, you are getting xz, and for signal yn, when you perform z transform, you are getting yz. The question also say yn is the upsampled version of xn with upsampling factor n by 3. Now let me write it down first, then we will see what it means. So if you refer to lectures of week 2 for Multirate-DSP, you can clearly find the notation. You will not have any problem with the notation. This denotes that upsampling is performed with the upsampling factor 3, and yn is the upsampled version of xn. What does that mean? Let me write it down. That means yn is going to be, okay, let me write a little bit clearly. X n over L for n is equal to 0 plus minus L plus minus 2L, like that. Basically it means multiples of n. It has a value of x n over L and it is 0 otherwise. So let us try to understand this by an example. Let us denote xn, this sequence we can write like this: -2 3 1 4. So if we draw xn in the discrete domain, how it is going to look like? It's going to be 3 at 0, 1 at n is equal to 1, 4 at n is equal to 2, and -2 at n is equal to -1. Okay, so let us try to find yn. So let me write xn here, values of yn here, and this is values of n. Okay, so if value of n is equal to 0, xn is going to be, okay, let me correct this representation so that it is easy to understand. Okay, fine. N is equal to 0, n is equal to 1, n is equal to 2, n 3, n 4, n5, n6. We'll check values of x and y at these points for xn and yn. So xn value at x n is equal to 0 is x0. Same for y. Yn is going to have value n is equal to 0 is same as x0. So we can write this as x0 only. Now value of xn at n is equal to 1 is given by this, that is x1. Now this 1 is not a multiple of L here. By the way, value of L, in this example L is going to be 3. So clearly n is 1 is not a multiple of 3, so yn is going to have a value 0 here. Next we move to n is equal to 2, where the value of corresponding value of x at n is equal to 2 is x2, which is denoted by this, that is 4. Again n is equal to 2 is not a multiple of 3, therefore yn will take value 0 again. Now I move to n is equal to 3. Now clearly xn is 0 for n greater than 2, therefore xn will take value 0 here. Now yn, now n is equal to 3, it's a multiple of 3, so therefore its value will be x of n divided by 3 at n is equal to 3, which is x of 1. For n is equal to 4, 5 and 6, x n values are going to be zeros. Now we move to n is equal to 4, which is not a multiple of 3, so yn is going to take value 0 again. And for n is equal to 5, not a multiple of 6, so again 0. For n is equal to 6, it's a multiple of 3, therefore yn is going to take value xn by 3, where n is equal to 6, which can be represented as x is equal to 2. Similarly on this n is equal to -1, I won't plot the values, I'll just plot the values, I'm not writing it here. So if this is the plot of x of n, now if I have to plot the yn, let me plot it, we are going to get something like that. So at n is equal to 0, I am going to get values of x0, then at point 1, I'm sorry, then at point 1 it takes value 0, at point 2 not a multiple of 3, so it again takes value of 0, at point 3 it's a multiple of 3, therefore it is going to take value x1, then again at 4 not a multiple of 3, so value 0, at 5 not a multiple, so 0 again, at 6 as a multiple of 3 it's going to take a value x of 2. Similarly on negative for n, it is not going to take any value at -1, I mean it will take 0 value, and -2 because these are not multiple of 3 anyway, -3 is a multiple of 3, therefore it is going to take this value. So if I try to denote yn in this way, it would be something like that, -2, 0, 0, 3, 0, 0, 1, 0, 0, 4. Now we can see that between any two samples of xn, we saw an introduction of pair of zeros. Now in generalized case you can refer to as L minus 1 zeros. So when xn is upsampled by a factor of L, it is, sorry, let me be more specific. The upsampling process is going to introduce L minus 1 consecutive zeros between samples of xn. So let me introduce a new slide here. Okay. Okay, I guess I did some insertion of slide in the wrong place. Let me correct it. Okay, I guess it's fine now. Therefore yn being an upsampled version by the L, of course, upsampling factor of xn have following representation. It is yn, as I mentioned in the previous slide, to be xn over L for all n for n not multiples of L. So let us see what the question says. What is the Z transform of Y in terms of X? So let me write the expression of xz first. Z transform of X, xn, z to the power minus n, when n runs from minus infinity to infinity. Now we can write yz first as the Z transform of yn as n runs from minus infinity to infinity, yn z to the power minus n. Now we see yn is going to be 0 for n not multiple of 3 in this case, because L is equal to 3. So yn only exists for n multiple of 3, so we can safely replace n for only kl. Sorry, yeah. So if yn is going to be 0 for all non-multipliers of 3, therefore we can safely replace n with 3k, where k is some integer in this expression without any loss of information, because for n not equal to 3k, yn is going to be 0. So this is same as writing yn, I am replacing n with 3k, z to the power minus, again we are replacing 3k when k runs from minus infinity to infinity. This step to this step, no loss of information, because for n not equal to 3 case, that is for all values of n which are not multiples of 3, yn is going to be 0. Now we can write y3k in terms of x as 3k over 3, because we see this equation, yn is x n by 3. Therefore if we replace n with 3k here, y of 3k is nothing but x of 3k over 3, z minus 3k. This results into k tends to minus infinity to infinity, x of k z cube to the power minus k. Now we can see the resemblance between this and this. This is nothing but x of z cube. Why? Because this n and k index here, they both runs from minus infinity to infinity, so it's just about notation, otherwise the expression is same. So if we want to write the z transform of yn, yz, in terms of z transform of x denoted as capital X of z, so it comes out to be y of z is equal to x of z cube. So 2 is the correct answer. So let us move to the third question. It's basically a fill in the blanks. It's about the impact of downsampling and upsampling process on the spectrum of any arbitrary signal. What happens, that which one contracts and which one results into stretching. So before getting into answer, let us understand. So we consider two things, that continuous time signal xt, its discrete version xn, we assume that Nyquist criteria is satisfied. So we just a minute. Okay, so we consider two signals. One is upsampled version of xn, denoted as yn, where upsampling factor is L, and another one is downsampled version of xn with the downsampling factor m, denoted as zn, and underlying its continuous time representation. Okay, let us skip the continuous time representation. We can do this all in discrete domain also. Let us consider signal xt is band limited to 2000 Hz. So we can draw the spectrum xc of j omega as this. In continuous time domain, of course, continuous time frequency domain. 2 pi times 2000 minus 2 pi times 2000. And let us consider the sampling frequency is Fs is 8000 Hz. So it's clearly oversampled. So in discrete domain, the spectrum of xn will look something like this. Spectrum of xn, which we are going to denote as x e of j omega, spectrum is going to look like this. There are actually multiple copies. I am not going to draw all. It's anyway periodic with period 2 pi. So we can see if sampling frequency is 8000 Hz, so 2 pi corresponding to 8000, therefore 2000 is going to correspond to pi over 2. So in discrete time spectrum, it's band limited from minus pi by 2 to pi by 2. Now if we upsample xn, like upsampling process, let us consider L is equal to 2. So let me draw the spectrum of yn, which is obtained as x of n by 2. I am removing the amplitude scaling factor as of now. We are just interested about this bandwidth thing of yn. So y e of j omega y e of j omega is related to x of e j omega by this equation. So this will shrink as this. I'll explain later, do not worry about that. This is pi, 2 pi is being mapped here, 0 is being mapped here, pi by 2 is being mapped here as pi by 4, because now y of e to the power j omega is x is equal to t power j 2 omega. So it's basically periodic with period pi, where x e of j omega was periodic with 2 pi, y e of j omega is going to periodic with pi. So you see what is happening here. The bandwidth was minus pi by 2 to pi by 2, and here it is pi by 4 to minus pi by 4 to pi by 4. So as a result of upsampling, the bandwidth is contracted. It creates the copies of original spectrum, but a contracted copies of original spectrum. So upsampler is going to contract the frequencies. Similarly, we will say what happens to downsampling case. Let me introduce a slide here. So now, instead of moving into discrete domain, let us consider the impact of downsampling in continuous time domain itself. So let me draw the spectrum of xt as follows for better understanding. Minus 2 pi times 2000 and plus 2 pi times 2000 minus 2 pi times 1000. Now sampled at a frequency previously at 800 Hz, which results into in discrete time spectrum like this. Of course, it's periodic with period 2 pi, and the bandwidth of the origin spectrum was from minus pi by 2 to pi by 2, because 8000 corresponds to 2 pi. Therefore, the maximum frequency content 2000 in case of xt is going to be pi by 2. Let us consider downsampling, that is, we are considering a sampling rate f dash of s which is half of previous sampling rate, 8000 by 2, 4000. Now if I move to see in discrete time spectrum, the spectrum will look something like that. Now your 4000 corresponds to 2 pi instead of 8000. Consider previously when our sampling frequency was 8000, 8000 corresponds to 2 pi. That is, it's our key to move from continuous time spectrum to discrete time spectrum. Now I reduce my sampling frequency, that is, effectively I have downsampled with a downsampling factor of 2. Now my sampling frequency is 4000 Hz. So now 4000 corresponds to 2 pi. Therefore 2000 will corresponds to pi only. Therefore the spectrum will look something like that. I am drawing only 1 copies on the both side of original spectrum. It actually gets repeated up to infinity. So now this pi by 2 is going to map into pi. This minus pi by 2 is going to map into minus of pi. So you can see for our original signal xt, the bandwidth here was minus pi by 2 to pi by 2. Now the original spectrum is spread in discrete frequency domain from minus pi to pi. Therefore it causes spread in frequency domain. Therefore we can say down sampling leads to spreading of frequency spectrum. Therefore the blank will be covered with contracts. Oh, sorry, not contract, it should be stretched. Let me correct myself. Downsampler stretches the frequency. Therefore the answer is going to be the second option. Okay, so let us move to the fourth question. Okay, let me introduce one more slide because we will need it later. I'm going to take a 2 minutes break here. It's an emergency. Please stay with me. I'll be back in 2 minutes. Okay, let us move to the fourth question now. Sorry for the interruption. So this is a slightly tricky question, like at least it looks like that. So let us see. This is a continuous to discrete time converter. This is a discrete time system, LTI system. Here you perform discrete to continuous time, which results into YRT. Okay, so it says that xt is band limited from minus 40 kilohertz to 40 kilohertz. Xc is band limited minus 40 to 40 kilohertz. Therefore, first let us draw the spectrum of Xc in frequency domain, that is Xc of j omega. Xc of j omega ranges from minus 2 pi times 40 into 10 to the power 3 to 2 pi times 40 into 10 to the power 3. Don't forget the units, radian per second. Okay, omega is continuous time frequency. Fine. We require that yr of j omega, which is spectrum of this output yr of t, to be xc of j omega for omega less than 10 pi times 1000. Okay, so the discrete time system transfer functions such that yr of j omega should look like this. Okay, the spectrum yr of j omega according to the question should look like this. It is 2. Okay, let me write it in the way as it's given in the question for conceptual clarity. 10 pi times 1000 minus 10 pi times 1000. Basically, we have to find the equivalent discrete time system which only keeps this portion of xc of j omega, and whatever is outside, in this region it should cut off. It's another way of saying we need to filter this portion. We need to filter this portion out by this discrete time system, which will cut off the rest of the part. Okay, so let us write the equivalent expression, the relation, input output relation, which is denoted as xc of j omega times h effective j omega. If you refer to lecture, you will find clear resemblance between what I am writing and what is there. The result should be yr of j omega, where h effective j omega is the equivalent transfer function of this entire system. Now h effective j omega is going to be h e, sorry, let me correct myself, h e of j omega for omega less than equal to this and 0 otherwise. Okay, where He of g omega is LTI, sorry, this LTI discrete time system channel response function is He of j omega. Fine. So basically we need to perform filtering here, and the sampling period t is given as 1 over 80 into 10 to the power 3. In other words, sampling frequency f is equal to 80 into 10 to the power 3. Fine. So let us move to the xt. You are sampled at 80 kilohertz. Therefore, discrete time spectrum will look like that: 80 into 10 to the power 3 going to correspond to 2 pi. Okay, let me draw xc of j omega here for reference once, which is band limited to minus 40 to 40. Minus 40 times 10 to the power 3 into 2 pi. 2 pi times 40 into 10 to the power 3. Therefore 40 into 10 to the power 3 will correspond to pi only. Therefore discrete spectrum xe of j omega dtft, we draw the spectrum like this. Where this corresponds to pi and 2 pi corresponds to 80 kilohertz. Now the spectrum of yr j omega is supposed to be like this only, as far given in the question. 10 pi times 1000 minus 10 pi times 1000. Okay, and let us move to the question once. The low pass filter response He of j omega should be like that. By the way, if you see the question, it mentioned ideal low pass filter. That is why we have the sharp edges here, that up to this frequency it allows everything below omega c, and it sharply cut off the frequency component higher than omega c. That is not going to happen in practical case, but as it's ideal low pass filter, this is going to represent it as that. Therefore, as per discrete to continuous time frequency relation, we get WC should be like this. omega m over Ts, where omega m corresponds to 10 pi times 1000. Why we are doing that? Because x e of j omega has this spectrum, and this filter, ideal low pass filter, is supposed to cut off this portion, where this should correspond to minus 10 pi times 1000 here, and 10 pi times 1000 here. So this ideal low pass filter, let me draw it with some other color. This ideal low pass filter should let this portion of spectrum pass through and cut off the rest of the part. So this point should correspond to the maximum frequency in YRJ omega, and by the relation between omega c, which is discrete time frequency, and omega m, which is continuous time frequency, they relate to each other via sampling frequency. So therefore this relation is dependent over sampling frequency, is another way of saying 1 over sampling rate. So here we can write here sampling rate. Therefore if the ideal low pass filter, this is called cutoff frequency. Why cutoff? Because this low pass filter is not going to allow any frequency greater than omega c to pass through. That is why. So let us find the value of omega c quickly. Omega c, therefore it's like 10 pi times 1000 divided by 80 times 10 to the power 3. So you get the cutoff frequency as pi by 8 radian of the ideal low pass filter. Therefore for this given discrete time system and given this sampling rate is very important. You can clearly see from this expression, if I change the sampling rate, therefore your cutoff frequency is directly going to be impacted. So for the same system, if we sample at different rates, the cutoff frequency of ideal low pass filter is going to be different. So for this case, for sampling frequency of 80 kHz, we need an ideal low pass filter with cutoff frequency pi by 8. So second one is the correct answer. Okay, this is pretty much straightforward. Let us understand it in details. Like you can tell the answer by saying it, but I would like to move in a more conventional way to get the concepts clear. So xn you write as 4, 2, 3, 5, 1. So let us consider it starts from here. So we can plot xn in discrete time axis like that. Xn is going to be, some plot of xn is going to be like this: 0, 1, 2, 3, 3 the value is 5 and 1 4. Oh, sorry, let me correct the index. Okay, now you are doing upsampling operation by a factor of 4. Let us denote this new sequence yn, which you can write as x of n by 4, because yn is obtained by upsampling xn with upsampling factor 4. Therefore, you can represent yn as follows. Actually, this is a crude way of writing, but this is not the actual expression should be, so you can ignore this. Yn is mathematically, in correct sense, is represented as x n over 4 for n 0 plus minus 4 8, like that, basically multiples of 4 and 0 otherwise. So if we saw in the example from previous slide that upsampling by a factor of 4 leads to not 4x, let me write the generalized expression here. If you upsample with a factor of L, it leads to L minus 1 consecutive zeros between original samples of, this is not the correct, so yeah, between samples of original signal. Okay, so in our case L is equal to 4, so it leads to introduction of L minus 1, where it is 4 minus 1, 3 consecutive zeros between the samples of xn. So if I am to plot yn, let us see how it's going to look like. At 0, it is going to be x 0 only. Then at index 1, as it's not a multiple of 4, its value is 0, so we consecutively introduce 3 zeros at 1, 2 and 3, because these are multiple of, not multiples of 4. And at 4 we have this value of x1, then again 3 consecutive zeros as we have seen before. Then again at 8 we get x is equal to 2. Let me write the indexes also for better understanding. Again at 9, 10 and 11, not being multiples of 4, the values of yn would be 0 at these points. At 12 it's going to have a value x of 3 equivalent to, then again at 13, 14 and 15, 3 consecutive zeros again. Then at 16 being multiple of 4, it would take value of x of 4. So if I want to write this as an array, it would turn out to be x of 0, which is 4, comma 0 0 0, 3 zeros, then x of 1, which is 2, then again we introduce 3 zeros, then again x of 2, which is 3, we keep introducing consecutive 3 zeros, then 5, then again 3 zeros, we get 1. So this is the expression of yn, not the expression, actually the output sequence yn is denoted as this. See which of the option matches. It's clearly option 1. Let us move to the next problem. Okay, it says consider the DTFTs of the input given to and output obtained from the system in the given figure. What can we say about the system? It says DTFT, discrete time Fourier transform. So let us consider input sequence xn. There is some system which we are unaware of what this is. We give input xn to this system and we get output yn. We consider dtft of xn as x e to the power j omega and yn, the DTFT of output sequence, as y of e to the power j omega. We are given these spectrums x e of j omega and this is x e of j omega, the input to the system. This is the spectrum of y e to the power j omega, which is output that we obtain from the system. Now the question asks that what possibly the system is going to be, whether it's a downsampler, whether it's a upsampler, whether it's a notch filter, whether it's a differentiator. Okay, so you can clearly see that the input spectrum, it ranges from minus pi by 4 to pi by 4. Okay, and we see the output spectrum is spread from minus pi to pi. So we have seen previously that downsampler stretches the frequency spectrum. Let us again try to understand it by some example. Suppose you are performing downsampling operation xn a downsampling factor of L, and you are getting this yn. So let us write the expression of yn. Yn is going to be x L of n. Therefore, you can see from this example, it is going to skip a lot of samples of x and going to take only a few. For example, if xn is something like this, like this one, this, this is plot of xn and discrete time. Now if you downsample it by a factor of 2, let's say, then it is going to pick this, it's going to skip this and pick this, again skip this, pick this. So therefore the downsample version of xn is going to contain something like this. It skips the sample completely in between. So if the DTFT of xn is denoted as x of e to the power j omega, you write it as x of n summation n tends to minus infinity to infinity e to the power minus j omega n, and y e of j omega, which is the DTFT of output sequence yn, denoted as n tends to minus infinity to infinity yn e to the power minus j omega n. This leads to, we can also write it as yn, we can replace as x l n e to the power minus j omega l n, and without loss of information we can denote this ln sorry, I made a slight mistake here. Let me correct myself. So as I was saying, I am replacing yn with x of ln e to the power minus j omega n. This can be, if I replace ln by some k, then k also runs from minus infinity to infinity, because if n runs from minus infinity to infinity, then k, which is nl, finite multiple of n, is also going to run from minus infinity to infinity. Therefore this summation results into k is equal to minus infinity to infinity x of k to the power minus j omega. Now n is replaced by k over l. Now you can say this expression is nothing but x of e to the power j omega by l. So you can see the compression of frequency happens when you downsample the signal. Earlier, which was omega, now it becomes omega over L. So to account for that, you need to spread the original spectrum. So it is because as omega becomes omega, sorry, I made a little notational mistake here. Yeah, so as the frequency content is compressed, the pi by 4 of input signal is going to mapped into pi by 4 times sampling downsampling factor, where L, if we take L is equal to 4, it becomes pi by 4 is mapped to pi for L is equal to 4. So basically when you downsample by 4, your spectrum, the spread becomes 4 times, and this maximum frequency content moves from pi by 4 to pi. So we can say it's a downsampling operation has been performed. The system is therefore a downsampler. Now we move to question number 7, which says which of the following will not suffer any loss of information upon downsampling by a factor of 2. Now if we refer to the lecture, if xn, you downsample it by a factor of L to get yn, the DTFT of yn, that we denote as y a to the power j omega, and if we denote the DTFT of xn x e to the power j omega, then the relation between y e to the power j omega is 1 over L, k runs to 0 to L minus 1, x e to the power j omega by L minus 2 pi by L times k. So basically you can see it downsampled signal become periodic with L pi, but any discrete time signal is periodic with 2 pi, so we cannot violate the fundamental conditions. So this results into copies of original spectrum with a amplitude scaling factor and frequency shifted version of the spectrums. So this is the relation between the DTFT of downsampled sequence and the original sequence. You get a scaled amplitude and frequency shifted verse copies of the original spectrum. Now if we take the k is equal to L is equal to 2, which is in this case L is equal to 2, so basically loss of information means it is equivalent to saying x e of j omega by 2 corresponds to k is equal to 0 here, this spectrum and its adjacent spectrum. Okay, let me write it more clearly. Corresponds to k is equal to 0 and its adjacent copy x e to the power j omega by 2 minus 2 pi, k is equal to 1, l is equal to 2, 2 pi over 2 pi, this shifted by pi corresponds to k is equal to 1. So loss of informations mean x of e j omega by 2 and x e j omega by 2 minus pi overlap. Therefore, if x e j omega by 2 and x j omega by 2 minus pi, the shifted version, if they overlap, then there will be loss of information, and if they do not, there will be no loss of information. So let us see the first option, which is xn, the shifted impulse n minus n naught. N naught is unknown, its frequency spectrum is basically going to, the value will be 1. Let us write the frequency spectrum. It would be like this, j omega n naught. So it will be spectral line at each frequency with a phase which is going to be different at every frequency and also depending on n naught. So its amplitude spectrum will be constant for all the frequencies. Therefore these copies are going to overlap, so there is a loss of information in this case. So first option is cancelled out. Let us move to option 2. Here you can let us write for first case, information loss will happen because of this condition. This and this are going to overlap. For xn is equal to cos pi n by 4 plus cos 3 pi n by 4. The frequency content in frequency domain we can write as 1 at pi by 4, another one is at 3 pi by 4. Now the shifted version, this is x e of j omega. One is at minus pi by 4, another one is at minus 3 pi by 4. Let us write x e to the power j omega by 2. What is going to happen? It just broaden the spectrum. Previously which was in pi by 4 will be now in pi by 2, and previously which were in 3 pi by 4 is now going to be at 3 pi by 2. Similarly here, minus pi by 2 and minus 3 pi by 2. Now the contents of x e to the power j omega by 2 minus pi shifted by pi. Let me denote its spectral contents with this blue line, which is going to cause an overlap. Let us see how. 2 pi, it would leads to, okay, let me use the eraser once. It will lead to spectral contents at these places also. This shifted version at pi minus pi. Oh, sorry. Let me undo this. This is actually what I have written is wrong. It is not at minus pi here. This shifted version are going to overlap on top of that, like this. Okay, so it is going to have overlapping of spectral content. Therefore, it would also lead to loss of information. Let us see the third one. So this also, okay, just a minute. Okay, let me introduce a new slide here. Okay, so this option is also not correct, like we will have loss of information when downsample with a factor of 2. Let us move to third option, which is xn given by cos pi n by 4. Let us draw the spectrum here. It will have spectral contents at pi by 4 and pi by minus pi by 4 and plus pi by 4. When you downsample it, the spectrums will shift to location given by pi by 2 and minus pi by 2. Now this spectrum and the spectral components of x j omega by 2 minus pi are not going to overlap, like there will be no overlapping between the spectrum of x e to the power j omega by 2 and x e to the power j omega by 2 minus pi. You can see that by plotting the spectrum of the shifted version. I won't do it. it's an exercise for you that these two spectrums are not going to overlap. So there will be no loss of information in this case. Okay, so the correct answer is this, 3 cos pi n by 4. Let us move to the question 8, which says a band limited signal is known to have a 60 Hz component that we want to remove by processing the figure below, where again the sampling frequency is given as 10 to the power minus 4. What is the highest angular frequency that can be present in continuous time signal if aliasing is to be avoided? Fine. Okay, there is some error in this question, I guess. Let me move to the next question. So again the DTFT to the input and output of a system are given. It is asked that what I think for the, you see the input spectrum is from minus pi to pi, periodic with 2 pi of course, and the output spectrum with pi by 4. So I am not answering it directly. Let me explain it with example. So if I have a spectrum, let's say x sorry let me raise it. Okay, the spectrum of xn in discrete time domain, discrete time frequency domain, is given as this. For example, this is pi, it's asymmetric, this is minus pi, and this is 2 pi, like that. So when you perform upsampling on xn to get output sequence yn, as I explained in a problem before, it contracts the spectrum. So if this is the spectrum of x e to the power j omega, let me write down the spectrum of y e to the power j omega, which we also can denote as x e to the power j omega L. So basically it going to contracts by a factor of L. How we are going to write that? So this 0 will remain as 0, this pi by L will correspond to pi over L, and this 2 pi will result into something like this. This corresponds to 2 pi over L. Similarly, 4 pi over L here. So let me okay, get some error. Okay, let me make a comment here. Upsampling by a factor of L introduces additional L minus 1 copies of contracted version of original spectrum in 0 to pi range. For this example, we can see these triangles have bandwidth of 2 pi. Now you see this pi is being mapped here at pi by 4. So you can see additional 3 contracted version of original spectrum has been introduced. Basically this was periodic with 2 pi. Let me write it down. Periodic with period 2 pi. This is periodic with period, we can see pi by 2. This is pi by 2. Therefore you can see that additional 3 copies are been introduced. So if I upsample by a factor of L, additional L minus copies are introduced. So if 3 copies are introduced, then I should have upsampled this input signal, input sequence by upsampling factor of 4. So therefore the answer is going to be the second one. We have upsampled with the upsampling factor of 4, which results into this spectrum. So this expression, you can see this is a transfer function where you can see that omega is equal to omega naught denotes zeros. Basically this is a notch filter, if you remember from the lecture. Where omega is omega naught. If omega at omega naught, you have 2 zeros, and you can see this factor of 0.9, that is somewhere here. F introduces a pole. The resultant transfer amplitude response of such a filter is going to be something like that, like at omega naught and a small region around omega naught, it is going to completely remove the frequency component. Ideally it should remove omega naught frequency component only, but in practical case that could lead to instability. So it removes omega naught and a very other frequency components in very close vicinity of omega naught, and it let pass all the frequencies. So it's basically a notch filter. So in the previous question, the angular frequency angular frequency. Okay, let me check once. What is the highest angular frequency that can be present in continuous time signal if aliasing is to be avoided? Okay, I guess some information is I missed here. So we considered the angular frequency from the previous example to be 10,000 pi here. So what should be the value of omega naught to eliminate the 60 Hertz component? We know the relationship between omega naught and angular frequency omega here by omega over, sorry, not omega, by Ts. It's omega times Ts, so it should be I'm sorry, in the previous example I made a error in the values. The sampling frequency, the sampling time in the previous question, Ts, was given as 10 to the power minus 4. So we know the relation between the discrete frequency and continuous time frequency. We want to remove the 60 Hz component, so corresponding analog frequency is going to be 2 pi times 60. So the value of omega naught corresponding to the 60 by 2, corresponding to the 60 Hz component in continuous time, the corresponding discrete frequency would be given as omega, let me write it down properly, omega naught is equal to omega, capital Omega time Ts. We calculate the values, we get the answer 3 pi over 250. So therefore first one is the correct answer. In 11 we have yn is equal to x n minus 5 delayed version of xn. So what should be the relation between z transform of yz and xz? To be specific, what is the value of a? So let us write the z transform of yz can be written in terms of an expression of z transform yn z to the power minus n, which is denoted as n tends to minus infinity to infinity x of n minus 5 z to the power minus n. Now we replace n minus 5 with m variable. If n varies from minus infinity to infinity, again the same applies for m also. So there is a slight change in index but nothing else. X of m, z, we replace the value of n here as m plus 5. So it is m tends to minus infinity to infinity z to the power minus 5 x m, I take the z to the power minus 5 out, z to the power minus m. This is nothing but the z transform of xn with a change in index. So therefore if we compare between this and this, we can find the value of a is going to be -5. So 1 is the correct answer. So let us solve the question number 12 here about upsampling system. Upsampling system, first we need to check the linearity property. Linearity property constitutes of two things, that is additivity and two, homogeneity. That basically means you have two sequences xn, you send via an upsampler L, you get the elevated version xe of n, and you send yn through a upsampling system, you get ye of n. Now if the system is linear, a scaled version of xn plus another scaled version of yn should result into should transform into same result in case of output also. Now you can see that upsampler satisfies this property. So upsampling is linear. Now to see time invariant property, let us denote a signal xn as 2, 3, which you can denote as like this: 0, 1, 2 and 3, and you upsample it the value L is equal to 3. That would result in upsampled sequence xn given as 2. You introduce two consecutive zeros, so this will be something like this. Xe of n. Now you see, you shift xn, like you perform a delay of 1 unit, x of n minus 1. The plot is going to be like this. It would be just shifted on right, delayed by 1 unit. One and 2. And if you perform upsampling operation over this, you are going to get upsampled version of n minus 1 as this. At 1 it is having non-zero value, at 2 and 3 it takes value 0, at 4 again it is going to take value of 3. Now if I delay this output by 1 unit, it it is going to result into this spectrum. One, two, three, four. Actually, I made a mistake in the first one. This is wrong. Let me correct myself. So this will result into a spectrum like this only. At 0, it now takes value of 0 by virtue of this. Then again 2 consecutive zeros at 1 and 2. At 3, it is going to take value of xn minus 1 and is equal to 1. Again 2 0, 3, 4, 5, 6. So you can clearly see that these two are not matching. That is, the output of xn minus 1 when passed through upsampler does not match with output of xn shifted by 1 unit. Therefore, upsampling is time variant. So therefore it is not time invariant, but it's linear. So second one is the correct answer. With this I end today's session. The question number 8, there is some information missing. I will check that, uh, do the math and upload the answer in the drive. So we'll meet again next week, Tuesday, same timing, 6 to 8 p.m. Thank you.